Good morning to everybody, and many thanks to organizer for inviting me here at the beautiful conference. Can you hear me okay? Okay. I realize that in the audience, the majority are theorists, and I pose here quite a general questions. And to address these questions, to address these issues, I will not prove any theorem. I must disappoint you. I will not be showing many formulas. Instead, I will, on example of several experiments in several particular materials, I will show how these quite general issues can be addressed, and the answer is not very, is not obvious. For those who study superconductivity, you may remember that opening book by Matisse of 1960s, where there is written recommendation to experimentalists who want to cook new superconductors, and there is written, I will cite what is written there, stay away of magnetism. So let's see how it is now. But it doesn't work. This work. This does. Okay. So I will show a series of pnictides or arsenides. Just for the beginning, I will start with simple superconductors, and all of them are semi-metals. There is no competing phenomena like spin or charge density wave. And I will, moving from top to down, I will show how interesting features appear when antiferromagnetic order coexist with superconductivity, and then how the ferromagnetic order can emerge on top of the antiferromagnetic order. These are specifically materials which I will study. All of them are layered almost van der Waals forces between the layers. Therefore, it's nicely material for experimentalists because you can exfoliate, you can make thin flakes and study them and so on. Now, all of them have either structure is just a layer with a huge distance between European layers, and the magnetism, which I will talking about, comes from a large magnetic moment of European atoms. Here are more complex materials which superconduct, and I will be talking about pure compounds with no dopants. So it makes the physical picture clear and helps to understand what is going on without any effect of impurities. Now, just to start with a very simple tin arsenide. This is a FCC cubic structure of sodium chloride, and it is regular semi-metal. You can see here holes and electrons, and based on the experimental RPS measurement, these are particularly our measurements, you can reconstruct the Fermi surface. Just a little bit more detailed analysis show that it is type 1 superconductor. To conclude this, you have to obtain the density and all the parameters of the Fermi surface. Almost with no doubt conclude that it's type 1 superconductor. Nothing specific, no puzzles. The next is tin for arsenic 3, and it is also semi-metallic. It has a nicely pronounced gap that can be revealed by scanning tunneling microscopy. Critical temperature is 1.14, and also this is type 1 superconductor. No puzzles, just for the beginning that these are pure semi-metals. Actually, we studied this because we expected to find out the effect of spin orbit coupling on superconductivity, to find something like odd type superconductivity, but we didn't find anything. So more interesting is the next material, which is tin, which is Europium tin to arsenic 2, and it also has a layered structure where layers of europium alternate with layers of tin and arsenic. The tin and arsenic supply electrons to the conduction band, and europium atoms are responsible for the magnetic properties. The huge distance, pay attention that it's a huge distance between the europium layers, so that magnetic lattice, magnetic unit cell is huge. It's doubled the crystal. And what is remarkable about this feature? When we study the magnetization, it seems to be quite typical. The material, all of these materials like europium iron to arsenic 2 and europium to europium tin to arsenic 2, all of them exhibit a very simple magnetization curve just from the textbook. It develops linearly until you fully polarize spin. And one can see that there is a spin polarization field slightly depend on the orientation. Either magnetic field is applied in plane, then it is easy magnetized, or when you apply magnetic field perpendicular to the basal plane, then the magnetization is achieved at a little bit higher fields. This is important. But what puzzled us when we first started studying this material, there is a tiny but still pronounced magnetoresistance. It's negative magnetoresistance. Further, I don't show the magnetoresistance transformed to quite usual orbital type omega c tau squared, just a positive magnetoresistance, where there's no puzzle. But this one is quite surprising. It is present in almost all of the materials of this kind. I will show you, or maybe later on, but just do believe me that this is a typical for the wide class of these materials. So some strange negative magnetoresistance. When this magnetoresistance was noticed in many preceding studies, and people didn't find a precise answer and make conjecture that it may be either, well, some people who wanted to publish their papers in Nature, they wrote that this is a consequence of a topologically non-trivial band structure. Other people refer to the axion insulator type structure, and other refer to the scattering of electrons by magnons. Magnons are should be here. Neither of these issues I will show you can in fact explain this quite remarkable magnetoresistance. Now, what I said that the materials are layered, therefore they exfoliated, and we prepared, we grow the bulk crystals and exfoliated to the thickness of down to 60 nanometers. It's about 25 atomic layers. The band structure, which we studied first of all, shows that there is no topologically non-trivial state. The band crossing are much above the Fermi energy, which is zero level here or below, but at the Fermi energy, there is no feature that can be associated with topology. The calculated band structure also confirmed that this is the same metal. There are powerful, there is a quite pronounced hole type pocket in the center of the Brillouin, close to the center, and electrons close to the periphery. In a zero field, the resistivity temperature dependence immediately confirmed that we deal with same metal. You see that there is a huge anisotropy, an order of just 2 orders of magnitude between the resistivity in plane and perpendicular to the plane. And it decreases down to the lowest temperature, with exception of this kink. The kink corresponds to the magnetic ordering temperature, which I will explain further. This is the Néel temperature. And rise here before the king is just a normal textbook behavior for associated with antiferromagnetic fluctuations. This I show just to confirm that we deal with the same metallic and no signatures of the topologically non-trivial states can be found either on band structure or transport properties. Nothing unusual. Now, what about the magnetism? The European atom the European atoms have 4 electrons, which are responsible for magnetism, and the 7 Bohr magnetons magnetic moment and spin 7.5, and this the source of the magnetic ordering. Now, it's interesting question might be addressed to young researchers, how to find out the magnetic structure. By saying magnetic structure, I mean both the order and the direction of the magnetic moments. So for several years, people discussed whether the magnetic moments of europium are directed either perpendicular to the plane or in plane. Just for the beginning, from the crystal structure, from the latest structure, you see that the smallest distance between europium atoms in plane, and therefore the order in plane. And the question is how the interplane ordering sets, and by the number one issue, how it is magnetic moments arranged in the space, and the second issue is who is responsible actually for the magnetic ordering. Standard way is to go to the Brookhaven or other laboratories where spin polarized neutron and do neutron scattering, and it is of course standard approach, but not necessarily it gives the complete answer. But actually applying common sense arguments and doing very simple measurements like magnetization, you can immediately understand the magnetic structure. You see that in plane, the magnetic field needed to saturate all spins, to polarize all spins, is smaller. Therefore, it's easy to polarize spin in plane, and therefore the spins necessarily have to lie in the basal plane, and a little bit harder to spin polarize magnetic moments when you apply magnetic field perpendicular to the plane. So we deal with the easy plane magnetic antiferromagnet. The difference between the red and black curve immediately gives you just a value of the anisotropy constant, which comes to the Hamiltonian when you analyze properties. Now, a little bit harder question is how to find out the well, if the spins of europium atoms are polarized ferromagnetically in plane, then the question is how they arrange in the perpendicular directions. Actually, in other words, what is the helicoid step in the vertical direction along the C-axis? And it also can be addressed. Well, of course, you can again shine your sample with the X-rays and study study reflection, analyze the data, but much simpler way is to take measurements of the AC susceptibility. Here is a textbook example how the spin susceptibility develops when you decrease temperature in a different orientation perpendicular to the plane and in plane. It differs in this material by a factor of 2. And it exactly, according to mean field arguments, exactly correspond to this argument K Fermi C over 2 equal to pi. And it means that the magnetic moments from layer to layer rotates by pi. Now we know everything. We can write down Hamiltonian, but instead I write almost the same in the free energy, which is the coupling constant exchange, and I don't specify here as the largest exchange in plane. I will not be talking about the in plane. Still, here is the also coupling in interplane, some anisotropy, which I explained how it can be extracted. The less important are demagnetizing energy, shape-dependent energy, Zeeman energy, which is also quite unimportant here. So everything can be found from experiment without going to Brookhaven or Oak Ridge. Now, what I was said in the beginning, that this magnetic resistance is tiny, but it's intrinsic to the whole class of materials. I don't show whole class, but just 6 various materials show similar parabolic type magnetic resistance, which in some materials it's about 6%, and in some other it's 20%. It's small. All of them are layered antiferromagnetic materials. Now, to address the remarkable suggestions that this is axion insulator, we tested the anisotropic. We changed from curve to curve. We rotated the magnetic field relative to the current direction, and we see no anisotropy. So this almost clearly, so it clearly shows that there is nothing like axion insulator state. It's no insulating and no axions in this material. The next is isotropy. It does not depend on the field direction as you normalize magnetic field to this magnetization saturation field, and then it becomes direction independent. So the magnetic resistance is isotropic. Isotropic, not only with respect to the direction of current and magnetic field, but also magnetic field relative to the crystal axis. And I already showed, but I want to stress that it is tightly correlated with magnetization. The magnetic resistance sharply vanishes when we fully polarize. So in the zero magnetic field, there is some additional resistance which is killed by a magnetic field, and then the magnetic resistance transformed to the classical orbital parabolic rise. These are the major features which need to be explained. And the isotrope, no, first of all, I list here the known mechanism for you to remember, which can appear in the ferromagnetic and antiferromagnetic and can be responsible for the magnetic resistance. The polaronic hopping in oxide gives you exponential dependence, which here is inapplicable because we have semi-metals and no oxides and no ferromagnetism just in a total. Giant magnetic resistance is the most favorable and the most used in even an application, the magnetic heads. But this magnetic resistance is stronger than isotropic. It is the most pronounced when the current flows across the layers of, say, iron and nickel. And so this is not the case, and now isotropic effect. The next is the colossal magnetic resistance in granular compound and antiferromagnetic insulator like europium, zinc, phosphorus. And since in our perfect crystal, we have a single crystal, there are no grain and no grain boundaries, so this is inapplicable. The magnon scattering is quite interesting, that usually people think about magnons, but in the antiferromagnetic metal, they produce a positive magnetic resistance. And the negative magnetic resistance appears only in ferromagnetic materials. And then it's proportional to minus H from exceeding some minor field. It originates from field-induced separation of the magnon scattering. And finally, Kondo scattering is proportional to log of T, but in our materials we see no resistivity versus temperature minima, no magnetic impurities, and so on. So that all the known mechanism of the magnetic resistance are irrelevant. And I stressed and showed the data that the effect which we want to explain is isotropic. And isotropy immediately prompts us to consider the simplest point like scattering. Point like scattering is always present in the material because the resistivity doesn't go to zero. But what happens when the electrons propagate in alternating environment with alternating direction of magnetic moments of European layers? They tend to redistribute in the real space. Here with the color orange and blue is schematically written how electrons try to redistribute in the real space. Some of them which have a spin parallel to European atoms move to this layer and other move to this layer. So in total, the psi function in the real space redistributes. And as you remember, in the Born approximation, the scattering probability is proportional to the force power of the psi function. And the redistribution in the real space immediately gives you an additional scattering. And this additional scattering is enforced at zero magnetic field due to the spin polarized layers, but it will disappear as soon as you spin polarize all European atoms with the external magnetic fields. And then after spin polarization, it will completely disappear. This is an idea of this mechanism. And the DFT calculations confirm that electrons indeed are redistributed. This is contours of constant electron density with spin along one direction and spin along other direction. You see there that they are spatially confined in close to the corresponding European layer. Now, a little bit more formulas. As soon as we understand the mechanism, we can write down Hamiltonian. It breaks down into 2x2 matrices where diagonal exchange splitting and off diagonal are hopping integral across the layers. As a result, we obtained psi functions, and they are symmetric and anti-symmetric combination, the corresponding eigenvalues, energy, which are a little bit split. And the splitting here will be a function of two parameters: the exchange splitting of the energy levels of the conduction electrons and a hopping amplitude across the layers. This one can be calculated, but this can be estimated from experience because it's difficult to calculate the hopping amplitude across the layers. And this is splitting, which is responsible for the effect, as I will show further. Now, as I explained, what happens with the T-node hopping amplitude across the layers doesn't depend on magnetic field, whereas exchange splitting does depend on magnetic field. It roughly can be approximated as exchange splitting in zero field and the ratio of the antiferromagnetic vector versus magnetic field as a function normalized by its zero field value. The antiferromagnetic vector is proportional to the square root of 1 minus h squared. And as a result, we obtain the correction to the resistivity, magnetic resistance, negative, parabolic, and its magnitude is dependent on the ratio of the exchange splitting and zero field, node signify the zero field, and T node is overlapping in the cross direction. Now, the parameter here is the gamma, which is the ratio of the exchange splitting to T node, the hopping parameter. This can be either estimated from experiment, the gamma value, and also can be calculated from DFT calculation partly. The magnetic resistance calculated according to this formula, behaves like this. It is not precisely just one-to-one comparable to experiment, but roughly it has the same magnitude and the parabolic shape, and some deviation from the parabolic shape noticed with the, as you compare with experiment, might be indeed associated with the minor influence of the same Magnon scattering, which you cannot eliminate. So we have here the parameter which is responsible for the magnitude of the effect from DFT calculations of the energy spectrum. Splitting, it's about 13 MeV. Spin, purely spin orbit split. Eligible here, the exchange splitting is the largest. As for T naught, it's hard to calculate numerically, but we can estimate it from experiment. Experiment and anisotropy, as I showed you, 2 orders of magnitude with the resistivity across the layers and along the layers, and T approaching 0. From this, we can estimate T naught, like bandwidth over square root of this anisotropy. It's about 42 MeV. That is actually all to compare with experiment, and as I showed here, it's about the same magnitude as calculated. So we observe about 6% magnitude of the magnetic resistance in European tin arsenide. For some other materials, it can be a little bit more and a little bit less, bigger or smaller, depending on this ratio for particular materials. On the top of this parabolic magnetic resistance, of course, you can add classical omega tau squared, omega c tau squared dependence, which is just additive on top of the negative magnetic resistance I was talking about. What's remarkable about this effect? So you see that the relative magnitude of the magnetic resistance does not depend on tau. It is produced by short scattering, and finally tau cancels out because it present in the here and in the numerator and denominator, and it cancels out. So the effect is, the mechanism is universal. It is not sample dependent, it's not disorder dependent, it's universal. That's remarkable. And of course, it's point because we consider point like scatters, so it automatically provides the isotropy of the effect. I wish to make conclusion in this section. So the negative magnetic resistance related antiferromagnetic crystals originate from exchange splitting. It's isotropic. Its magnitude is disorder independent. It's universal for quasi-2 compounds. Its magnitude depends on the exchange splitting and interlay transfer integral. And of course, this magnetic resistance is tightly related to the antiferromagnetic magnetization. As soon as you as soon as you fully magnetize the European spins, the magnetic resistance disappears, vanishes to 0. Now, just for young people here, I wish to stress that shortly this universal isotropic nearly parabolic magnetic resistance originate from point-like scatterers and exchange splitting. I believe that the puzzle is mainly solved. Well, of course, we can add to this naive picture, we can add second order correction, add magnons and so on, just to fit experimental data precisely to the theory, but it is not very interesting. And I listed here a few materials where the same effect can be explained. So I believe the puzzle is solved. Now, let me move further to more interesting issue, which is coexistence of superconductivity and magnetic ordering. This is the old issue, very old issue, and the materials which we studied can be considered as a two blocks which are put on the top of each other. The 1, 2, 2 with the iron arsenate and rubidium iron arsenate here. So they compose a two-stage building. And there is, of course, the problem is rather old. As I said in the beginning, 80 years ago, it was considered that superconductivity and magnetism are enemies and cannot coexist. Then a lot of materials were discovered where magnetic ordering temperature starts at higher temperature than the superconductivity. It means that a magnetic ordering is stronger than superconducting pairing. And in this case, only p-type symmetry survives, and this is observed in uranium, germanium, uranium, rhodium, germanium, and uranium, cobalt, germanium. So we have a fermionic superconductor. But here we have a different case. In this compound, we have a different case. The superconductivity is stronger than the magnetic ordering. Because of the layered structure, the europium layers are far away. Therefore, the coupling is weak. So the magnetic ordering should emerge inside the superconducting state. For all these materials which are representative of the white class of iron pnictides, the pairing symmetry is believed to be S plus minus and happens mainly as a result of spin fluctuation. And the other parameter is multi-component as in any other multi-sheet semi-metal. And as I already explained, that interlayer ordering is of ferromagnetic origin because the europium atoms sitting close to each other, and intralayer and interlayer ordering is antiferromagnetic ordering. And it's an interesting issue to discuss who is responsible actually for this super exchange order. Additionally, there is a europium iron coupling, but it is a second order effect. The major problem here is to understand how these two phenomena coexist. But let's first study how the features are pronounced in experiment. This is layered and consists of layers of europium atoms, rubidium atoms, europium, and in between them are iron and arsenic layers which supply electrons to the conduction band. So the crystal is layered. When you cleave, it can cleave either on a europium plane or rubidium plane. The rubidium atoms are large in size, therefore it happens more often. But in any case, it doesn't cleave here, and therefore it doesn't allow you to have access with the tip of the scanning tunneling microscope, have access to the superconductivity. So it's impede the measurements of the superconductivity. Okay. Here, from resonant gamma scattering and elastic break diffraction, it was found that the step size in the helicoid structure is pi/2. It's interesting. Nevertheless, it doesn't change the physics. When we study resistivity, it shows a nice superconducting transition at 37 Kelvin. This is the high temperature superconductor. And inside there is, in the magnetic response, there is a tiny kink due to Néel ordering. And it also can be found in spin susceptibility measurement. Just you can analyze this and find that it is has a ferromagnetic sign because the ferromagnetic ordering is stronger. Now, the band structure is typical for iron pnictides. I will not show detail. There are, in the center of the brilliant zone, there are several hole bands and the electron bands on the corners. So nothing specific. What is important is to compare the levels which are responsible for magnetic ordering. They are lying far below the Fermi energy. Fermi energy somewhere here. The magnetic layers, europium 4f electrons are located at minus 1.8 electron volts below the Fermi energy. This is correspond to calculations. Also verified in doing scanner tunneling spectroscopy in DI over DV. You see here a feature responsible for features which is coupled with, which is explained by the density of states in this almost flat band. So everything is clear, and then it's interesting to see how the superconductivity develops here due to RPS measurements. We can trace the development of the superconductivity, how the gap changes, how the gap opens in any specific point of the Fermi energy. And I have a movie, but maybe I will skip it. Nevertheless, this is a typical profile of the energy spectrum when you go along one of these white arrows. So electrons, which here are sitting in the gap, and they are relocated as soon as the superconducting gap opens. And this is a typical superconducting behavior. You see here in the movie how the electrons redistribute when the superconductivity starts. So 40 Kelvin initially is above the superconducting temperature, and 4 Kelvin is deep in the superconducting state. Now, we applied a lot of efforts trying to find the effect of the magnetic ordering on the superconductivity, but in RPS we didn't see anything. The gap, 3 gaps extracted from this RPS measurement didn't show anything at the temperature of the antiferromagnetic ordering. This was surprising. Scanning tunneling spectroscopy didn't help, but we did Andreev multiple reflection with more resolution to test what is going here in the vicinity of the antiferromagnetic temperature, and we find actually no changes. So the superconductivity seems to ignore completely magnetic ordering. This was strange. This was strange, and this is one of the issues I want to discuss. Now, just a summary of what I have shown, that energy levels of the Europium 4F electrons, which are responsible for magnetism, are far away from each other in energy by 1.8 electron volts. And in real space, they're also far away of each other because the crystal is layered. Therefore, the order parameter amplitude maybe doesn't feel the antiferromagnetic ordering. But on the other hand, these arguments are not entirely address the issue. Indeed, the europium layers are sitting far away of each other, and direct dipole magnetic exchange interaction is ineffective. So electrons should somehow be responsible to change them to spin polarized. But if the electrons transfer the magnetic moment, how they at the same time participate in Cooper pairing? This was the question which we would like to address. But it is already clear that, but let's analyze this issue. To analyze this issue, we have to consider actually what mechanism is responsible for interlay exchange. As I said, this can be easily estimated. We need to explain the exchange coupling of minus 0.2 MeV, which comes from the Néel temperature, or comes from this magnetization saturation field. Anyhow, we know the magnitude, and we have to find out the mechanism which is responsible. We can make estimations, and the first, we immediately find that the direct interplane magnetic dipole interaction is 100 times weaker. It is ineffective. Then indirect RKKY exchange via the conduction of electrons, the issue that bothered us, is also quite tricky because it depends exponentially, it decays exponentially with distance, and moreover, it oscillates. At the given distance between europium atoms, europium layers, it is of ferromagnetic side. So therefore, the conduction electrons are not actually effective in setting the magnetic order. And this explain, and this may be most clearly explain how the superconducting parent and magnetic ordering, how they how they coexist. Now, the most important is super exchange between European layers via the non-magnetic localized electrons with the P and D states of deeper shells of tin and arsenic. Now, since we decouple antiferromagnetic ordering and superconducting parent, then are they indeed completely independent? Seems to be so, but in fact not. The ferromagnetic ordering does not affect the superconducting order parameter, but it does affect the density of the condensate. It can be measured by by either HC1 with the magnetization probe, or from critical current, which is 1 over penetration depth, and also depend on the density of the superconducting condensate. And it shows some features at the at the temperature of magnetic ordering. That's I guess with this issue we understand everything, and we understand how the electrons in this compound, how they split into teams, and one team is responsible for magnetic ordering and another for superconducting parent. Now I want to move further to the simple non-superconducting material, which is European tin arsenic, to ensure that despite this is a very simple non-superconducting semi-metal, it has several remarkable features. When you look at the literature and find in numerous papers, you notice that the behavior of the spin susceptibility is quite wonderful. You see that when temperature approach to 0, the susceptibility instead of saturation tends to diverge. And this is, of course, not the behavior typical for antiferromagnet. It points at some signatures of the ferromagnetism. What experimentalists often do, they apply magnetic field, maybe below 1 Tesla, maybe 0.2 Tesla, and then it is washed out, and seems to be a nice picture which may be published. But in fact, the question exists. Some people refer to maybe residual magnetic impurities, may be responsible for this ferromagnetic type behavior and susceptibility. In some samples, during measurements, you can notice a weak hysteresis. So what I want to say that in all the materials, all layered antiferromagnetic materials, you may find the signatures of the ferromagnetism. To explore this issue, we have taken the crystal, single crystal, and we didn't apply a magnetic field like this, and we see a huge manifestation of ferromagnetic behavior. Of course, when you apply it to 0.2 Tesla, you immediately wash it out and get what is reported in many papers and literature. Furthermore, we take precise measurements of the magnetization curve and found in the tiny vicinity of the 0 magnetic field, we found ferromagnetic type hysteresis. It saturates and vanishes. It saturates fully in field which are much less than saturation field of antiferromagnetic. So we clearly see signatures of the ferromagnetism in our clean sample. So we cut, using focused ion beam, we cut the lamella 15 nanometers thick and put in a transmission electron microscope. And we found that there are some strokes. These strokes, each of the strokes represent a planar defect, about 1 atomic layer thick. And what is specific here in this defect. The distance between the European layers, the white balls, is by 20% lower. The profile also shows that inside the defect layer, there are some additional weak but still additional row of Europium atoms, which are sitting not in the same at the same distance to the electron beam, somewhere further away. And the most important, most remarkable, that the tin atoms here missing. And nothing changes with the arsenic. Immediately, we tested the valence state of europium, because the europium can have a different valence state. Nothing specific, nothing unusual here. It's standard 2+ oxidation state. And just by decomposing this defect, well, this picture may show you how by doing micro EDX scanning, you can see what is going here on europium distribution, tin distribution, arsenic. So europium atom exhibit an additional row, tin is missing here, and arsenic is usual. And here the profile of this scanner showing the picture in details. Now, oops. Having all this data, we identified the crystal structure of the defect, and it is very interesting that it has a different formula. The formula here is europium, tin, arsenic 2. So the tin here changed the valence. Usually it has a 2+ valence state, but in this compound it is 4+. This compound is known in literature, and it has a cubic crystal structure. To match the cubic crystal structure with the orthorhombic crystal, it's not easy. You have to rotate cube by and have a diagonal plane 1, 1, 1 to match the orthorhombic structure. So in total, by doing all this transformation, you obtain the minimal supercell or transition layer, which describe the transition from the regular cell to the defect cell, and it has 33 atoms, and is of this is this content: europium 7, tin 12, and arsenic 14. So roughly, it's a europium, tin, arsenic. Now, if you have in the primitive cell, you have an odd number of europium atoms, you certainly will have a ferromagnetic ordering. Indeed, numerical calculations, and this just common sense argument shows you that you will get an 1 Bohr magnitude per formula unit of the ferromagnetic moment. This is confirmed by DFT calculations, which indeed show this ferromagnetic moment, and I list here conclusions of this measurement. The ferromagnetic-like features originate from not from impurities, but from lattice defect. You see that the crystal is grown, is synthesized and grown at temperature about 1000 degrees, and at this temperature, it's quite probable formation of different phases, which have a thermodynamically closed enthalpy of formation. So this is a typical result of all layer compound, where the planar defect can be easily formed. So the planar defects are inherent in many layered compounds due to very close formation enthalpy. And in our case, which we studied, the defect supercell contains an odd number of europium atoms and is ferromagnetically ordered. So the mystery of ferromagnetic type behavior is solved. And let us test how it may be pronounced in measurable properties. So we turn back to our measurements of the electron spin resonance, which we did in 2024, and we observed there in this same material, we observed instead of one resonance line, we observed two resonance lines. This is typical for antiferromagnetic, and this was completely unclear. So we couldn't understand the origin, and we only concluded that this has nothing to do with optical antiferromagnetic mode. And now we apply the picture, the naive model of ferromagnetic planar defect embedded into the bulk crystal, and try to understand this behavior. With the antiferromagnetic acoustic resonance, nothing changes. We have here all parameters known from the magnetization curve, no fitting parameter. We can explain, we can fit our measurements field depends on the resonance line with no fitting parameters. As for the unknown line, which we now attribute to ferromagnetic resonance in the antiferromagnetic crystal, we apply the textbook behavior. And we also can, there is one parameter which is responsible for, which is magnitude of the magnetization of the defect layer in our case. It can be taken from experiment or maybe used as a fitting parameter. They're about equal, but we prefer to, they're comparable. We prefer to use as a fitting parameter is 10 times smaller than the antiferromagnetic magnetization. So we use this fitting parameter and obtain quite reasonable fitting. Now we did also temperature dependence measurements using a cavity type spectrometer with more sensitive. Therefore, we were able to trace the resonance up to almost room temperature. And you see how the ferromagnetic resonance develops and merges here with antiferromagnetic resonance, and further they go as a single paramagnetic resonance. Now, to describe the temperature dependence for the antiferromagnetic resonance, we use a standard textbook formula where BG is the Brillouin function of magnetic field over temperature. For the ferromagnetic resonance, we also take textbooks formulas. There are two inputs. One can be, one follows from first order expansion in the vicinity of a critical temperature like this. And another is the Bloch law, which is applicable in the T approaching zero. Everywhere we apply the magnetization in a zero field, as I said, 0.13. And what happens as a result? We have a model that qualitatively is similar to what we observed in experiment. I didn't put on top of, didn't show together this curve because quantitatively they're a little bit different, and it is quite understandable because our model is very naive. It presumes that the two ingredients are completely independent and don't interact. So I believe that we understood that the ferromagnetic resonance indeed develops as due to the planar defects. The amplitude of this tiny planar defect, the ferromagnetic resonance is comparable to the amplitude of the antiferromagnetic resonance because the integral intensity is quite comparable. So I believe that the mystery is solved, and I suggest for young attendants the take-home message: the magnetic ordering versus superconducting pairing, and also the antiferromagnetic and ferromagnetic ordering, they necessarily compete or struggle with each other. They may go along, and I present examples when they cooperate and can even be aliases, but this I don't have time to speak more about it. I thank you for the attention, and many thanks to my co-authors for the collaboration. They are listed here. Thank you
very much. So what, by the way, where I was telling about the tight connection of Vladimir with Urals, I had forgotten to say that last year he has got a most prestige award and scientific award, Lebedev Award, and award ceremony was in Ekaterinburg, and Sergei Streltsov was the person who was representing Vladimir during the ceremony. Okay, questions and comments. Yes, please.
I would like to ask a question concerning the first part. Yeah,
The last part.
concerning this mechanism of magnetic resistance,
Mhm.
which you suggest in antiferromagnets. As far as I understand, the story is like follows. We have, for instance, two layers, two channels. And indeed, if the tunneling between the channels is forbidden, then putting an obstacle, a scatterer in one channel, you just prevent transport. You increase resistance. As soon as you switch on tunneling between the layers, then, of course, electron gets the possibility to go beyond the scatterer, just to increase conductivity. But the point is that scatterers maybe are not they are correlated. I mean that scatterer in a single layer, it affects the transport in the neighboring layer.
Look, I shown you that anisotropy in the resistivity is 1/200. So that means that the electrons propagate along and almost independently along the one layer and almost independently. The electrons propagate in the tunnel between the bottom and the ceiling of europium atoms polarized oppositely. That is the point. And they don't fill the next story. To go to the next story, the probability is 1%. So they propagate along in the tunnel,
Okay,
being split in real space, being separated in real space.
Yep. More questions, comments? And maybe, yeah.
Yeah, I'm really sorry. I didn't really get about the exchange constants. So they were calculated from Benicio, or they were like you showed a very nice comparison to this experiment, and you could fit the magnetization curve and a lot of things.
The spatial distribution was calculated by DFT from ab initio. But other is just the first order expansion.
Okay, and I did get, so you struggle about that small exchange, like 0.2 megaelectron volts, right? So was it in plane or interplane?
It is interplane.
Interplane.
Interplane,
then this
it's
is
interesting issue, but we don't see this, no sequence in the experiment. It should be larger.
Okay. Think much.
Maybe I will just make a very short note. You see that basically, it's more appropriate nowadays. You can use ab initio calculations, put all the parameters, we know all the spacing, we know magnetic moments. You calculate the band structure, then you numerically solve Boltzmann equation, put everything. This might be in 1 month of heavy work, you understand the answer, but you cannot understand what is responsible, which physics is behind. So therefore we did not a numerical calculation. Some people even calculated the magnetic resistance in this way.